Alright, electrochemical cells. When you look at the reactions, right, and we already talked about permanganate being reduced to manganese 2 plus, iron 2 plus being oxidized to iron 3 plus, and we figured out the balance reaction and we determined the potential of the cell, which ended up being positive 0.74 volts. Anytime that you get a reaction, a redox reaction for which the potential is greater than 0, you're looking at a process that's going to happen spontaneously. And moreover, this particular process where the cell potential is greater than 0, we refer to as a galvanic cell. And what this means is that the moment you combine those two reactants, they will react with each other spontaneously to give you the products. On the other hand, if you look at the opposite process, let's say that you're going from manganese 2 plus to permanganate, and you are trying to reduce iron 3 plus to iron 2 plus, then you have the same values except that the signs are exactly the opposite for each one of the two steps. And so you end up with an E cell that is negative. Now, this tells you that the process will not happen on its own, it will be non-spontaneous, and the cell as a whole will refer to as an electrolytic cell. So positive potentials, galvanic, negative potentials, electrolytic. And this is for the full balance equation, reduction plus oxidation combined. So let's take a look at the galvanic cells in more detail. Alright, so here we're looking at a copper and zinc example. We have the copper 2 to copper 0 reduction, and we have the zinc 2 plus to zinc 0 reduction as well. Alright, so looking at the values and starting with the reagents, copper 2 plus does not overlap with zinc 0, so that means that they will react with each other. And they will react in this particular case to give you copper 0 and zinc 2 plus. Here we have no question about that happening. Those are the only possibilities. And copper 0 and zinc 2 plus do overlap with each other. So this looks like it's a reaction that will happen spontaneously. So looking at the overlapping aspect, right, the fact that the reactants don't overlap and the fact that the products do overlap, that tells you that this reaction will happen spontaneously. And specifically, since zinc is technically being oxidized, you're going from zinc 0 to zinc 2 plus, you have to change the reduction potential, you have to flip the equation, and you have to change the sign for zinc because that's technically the oxidation. When you add up those equations together, you add up the reduction and oxidation potentials together to tell you that the cell potential is 1.10 volts, which tells you that this process is a galvanic process and this is a spontaneous reaction. Now, the fact that the reaction is spontaneous means that by combining those two chemicals, you can basically have electrons being exchanged between them. But if you were to simply add them together, that wouldn't really get you anywhere. You just produce the products. So what we do instead is we separate the two reactants and we connect them with wires. And we allow the electrons to flow through the wires. And this is basically the process of electricity, which, you know, if you've taken physics, you're probably even familiar with your electrical diagrams containing your current, containing your voltage. This is basically where you apply Kirchhoff's rules, which to some people, even myself included, can be a little bit complicated. But pretty much the electron movement in this wire is what we call the current. And one thing to keep in mind is that electrons, because they have a charge, they have a charge of 1.602 times 10 to the negative 19 coulombs. In 1 mole of electrons, right, which you can basically do the conversion, this is the charge per electron. To convert that to moles, we basically will have to multiply this by 6.022 times 10 to the 23rd electrons present in 1 mole of electrons. And this tells you that you have in 1 mole of electrons a total of 96,485 coulombs. This is known as the Faraday constant, 96,485 coulombs per mole of electrons, which will allow us to basically switch over from the amount of electrons we have to a total charge that we're distributing. We're going to definitely be using that a little later. Another thing that I need to point out to you is that the current is not simply charge. It's actually charge that's changing because you're moving it through a wire. It's actually the rate of change of current, which means that you're looking at charge over time. And specifically, charge in coulombs over time in seconds is what we call the amps. So the current has units of amps, but you want to think of amps as being coulombs per second. We're going to use that a little bit later. All right, so as I was telling you, if you mix your copper 2 plus with your zinc metal, it will react right away, but you won't be able to exploit the movement of electrons. So instead of putting them in the same compartment, you could actually place them in separate compartments and connect them with a wire to allow electron flow through the wires so that the spontaneous reaction proceeds forward. So here is, by the way, two metal pieces, which are what we refer to as the electrodes. You need to have some solid material to actually connect to the wire so you can exchange the electrons. So in this particular simple example, you're using copper metal itself, its own electrode, and you're using zinc metal also as its own own electrode. But in other instances where the reactant products may not be solids, you have to use other electrodes that don't form part of the reaction. Typical ones are platinum or carbon electrodes. And the solution right here, the blue solution, is a copper 2 solution, copper 2 nitrate, and down here you have zinc nitrate in the solution. So you kind of have to have the species present, and in addition to that, there is a something known as a salt bridge, which ensures that there is no buildup of charge on either of the beakers in this example. And if you want to, you could also connect the wires through a voltmeter so that you can actually see the potential change. And this is how we can actually determine the cell potentials of reactions experimentally. All right, now, chemically speaking, what's happening is that in the zinc compartment where the oxidation is taking place, the zinc metal, so basically the electrode, is being oxidized to zinc 2 plus, which goes into solution. But in the process, it loses electrons. And on the compartment right here where the reduction is happening for copper, copper 2 plus accepts the 2 electrons and becomes copper metal. Alright, and this is the reduction. Now I told you that the reduction is known as the cathode and the oxidation is known as the anode. And the reason why is because in the anode, as you're losing electrons, right, the electrons are not going to be in the solution. They're going to go into the wire and they're going to take off. As the electrons take off, this compartment here, the anode compartment, becomes positively charged. And by the same logic, the compartment with the copper is receiving electrons. So as time goes by, this compartment is becoming negatively charged. So what happens is that the salt bridge that contains a neutral salt, because the compartment where the copper is being reduced is becoming negatively charged, the sodium cation goes towards it to balance the charge. And because the cation goes towards this compartment, the compartment is known as the cathode. And over here, the compartment where the charge is becoming more positive and more positive attracts the anion. So the anion migrates towards it. And because the anion goes to this compartment, the compartment is known as the anode. So that's the reason why we call them that, right? Wherever the cation goes from the salt bridge, that's the cathode. Wherever the anion goes, that's the anode. But to put it simply, anode will always be associated with oxidation. Cathode will always be associated with reduction. Alright, perfect. Alright, so let's talk about batteries really quickly. So batteries, right, so here you have a 9-volt alkaline battery. And the idea is that one terminal of this battery has, you have your potentials, right? You have your plus and minus signs, which actually represent where the electrons are coming and going to. But in essence, the battery is actually a very well put together, very compact, but very well put together set of reagents, chemical reagents that spontaneously are meant to react with each other. So for instance, we have cobalt in the 4 plus oxidation state in the form of cobalt oxide as a solid, and then we have lithium metal. Alright, so this is basically a lithium battery. And neither of those two species overlaps with each other, so they actually do react to give you a species that overlaps. So lithium turns into lithium plus, which overlaps with any of the species here. So the cobalt 4 plus turns into cobalt 3. Alright, now the actual event that's happening, right, if you look at this, the lithium couple, right, the reduction from lithium plus to lithium zero is -3. So going from lithium zero to lithium plus will be +3. And going from cobalt 4 plus to cobalt 3 plus takes a potential of 1.42. So altogether, 3 plus 1.42 is about 4.42 volts. Alright, so that's what you get for the couple of lithium 0 with cobalt 4. And so you get from that 4.4 volts. But as you may have noticed, this is a 9-volt battery. And what that tells you is that, well, basically, what you're doing is you're assembling two of these setups in series, because when you do have batteries in series, or I guess you could call it I guess you could call it the electrical setup. If you have it in series, what ends up happening is that you end up adding the potentials together. So you actually have two of those cobalt lithium setups in series to give you an overall value of 8.84, which is, why this called this, we call these batteries the 9-volt batteries, right? They go up to 9 volts if you go with one sig fig, right? But technically, because the reactions are spontaneous, and we know they're going to happen spontaneously because cobalt 4 plus and lithium 0 don't overlap. So this reaction wants to happen. So what also has to take place in this battery is that you keep the cobalt 4 plus and the lithium 0 in separate compartments. They cannot touch each other, otherwise the battery will completely de-energize by itself. So you keep them in separate compartments, and what you do is you allow the little plugs right here that will connect to whatever apparatus you have to complete the circuit. And it's through these outlets that you allow the cobalt 4 plus and the lithium 0 to actually connect. So you allow electricity to take place as a result of electron flow. So technically speaking, a galvanic cell is a battery, and vice versa. And so your electrolytic cells, which are the ones that don't happen spontaneously, are going to be setups in which your reactants are overlapping to begin with, like copper 0 and zinc 2 plus, they're overlapping to begin with. So this doesn't want to react to give you products that do not overlap, because that will go against what they're trying to do, right? So your copper going to copper 2 plus, which is the oxidation, and the zinc 2 plus going to zinc 0. If you look at the potentials for those values, you're going to end up with a negative 1.1 volt value, which doesn't help you. That's not good for anybody. So for you to carry out this particular process, you're going to have to put in energy. And in other words, what that means is that you're going to have to apply technically a battery to this specific setup, right? The electrolytic cell does not want to happen on its own. So you could actually have them in the same beaker. They're not going to react with each other spontaneously. You have to literally hook up a battery, or at least an energy source, to this setup to allow this to happen. And specifically, you want to have a battery that has a higher voltage output as the voltage required to carry out the non-spontaneous reaction. So that's how you make this happen. Now, specifically what takes place here is that the positive terminal of the battery is attracting electrons. The negative terminal of the battery is supplying electrons. So you basically have the oxidation in your electrolytic cell, which is basically your anode, and your cathode compartment, which the reduction takes place, being lined up with the positive and negative of your battery. Now, technically speaking, at the positive terminal of your battery, that's your cathode. At the negative terminal of your battery, that's your anode, right? So sometimes this can get a little confusing because you're basically combining anode in the electrolytic cell with cathode in the galvanic cell. And you're combining the anode in the galvanic cell with the cathode in the electrolytic cell. But in both cases, wherever the oxidation happens, that's what we refer to as the anode. And wherever the reduction happens, that's what we refer to as the cathode. Alright, second thing is that this is going to create a current that you can measure in amps. And amps, once again, is given in coulombs per second. That's the same thing. And the other thing is that we can determine, based on how much charge we're supplying, how many moles of electrons are being exchanged. So the time of applied current is going to ultimately be associated with the moles of electrons transfer. and this is something we're going to investigate in the next video. So let me stop this process right now, and on the next video we'll talk about electroplating.